Hi, my name is Daniel. Welcome to the OSFC. And today I'm going to introduce Fiedka, the firmware editor, which is a graphical application to browse and edit firmware images. Here's the quick agenda. I'm going to introduce myself and the project a bit, talk about the scope of the project. Then we will see what the current state is, what the current capabilities are, and head over to a roadmap and how you can contribute yourself also to the project. So this is me. I have a few backgrounds in numerous topics, mainly IT security and computer science, but I'm working in practice as a software engineer currently, mostly on web applications, sometimes also a bit of infrastructure. And I've specialized thusly mainly on applications and user interfaces. I also work a lot in the open source space. I do hardware and firmware stuff, which brings me here to the conference. And I also work a bit in operating systems and software distributions. And occasionally I need to do some reverse engineering. And this is Fiedka. Fiedka is a graphical firmware editor. So it is an application in that sense. And it allows you to explore current firmware images, which is for now focusing on UEFI, as well as PSP and ME. That is the platform security processor and management engine file systems that you have in most laptops and servers and so on today. There is a work in progress for flash usage visualization. So besides the firmware image itself, you can also see the actual block usage, which we'll have a look at later. There is a TPM event log visualization, and that will be also covered in the roadmap later on. Planned are features for platform state investigation and secure boot key management. And here's a bold statement from Brian Cantrell. I usually used to define firmware as being whatever is already in your laptop or server, which allows you to run your actual operating system. So it would initialize the platform. But Brian said it a bit differently. He said it's software that is hard to get to. And that is actually one of the key selling points, if you will, for Fiedka, because I want to change that and make it easier to approach firmware. And that leads us to talking about being more agile and more open. So when working on web applications, I often had the issue that especially the UX and UI design folks that I was talking to were mostly using proprietary products and not very much used to more agile and open projects where you would more work on a collaborative project, but they were rather used to something like a waterfall setting. And I sense that the same is also true for hardware design and manufacturing. And so both have this one thing in common, which is a high amount of complexity. But I also see that both industries are learning a lot about agile and open processes so that they can improve and get earlier feedback, both from customers, but also developers, which are part of the process. And here's the next bold statement. I say that we need more tools and feedback, even though we already have a lot of tools. And my reason for that is that most tools that we currently have are usually very special purpose tools. Now we'll come back to that later on. But why do we need that? So especially for education, so we want to speed up the understanding that we have for a very specific field, like firmware, for example, which is very, very complex. So we need to be able to grasp everything that we see. The second thing is for research. So for security, one key point is transparency. And we can only get that if we have a very good understanding. And last but not least, of course, in development, if we want to have the ability to develop in a sustainable manner, that is, we want to maintain things over time, we also need to maintain our understanding. So especially in fields where there is a lot of complexity and change over time, it is easy to lose some of the understanding that we had at some point. So it's always good to have any assistance that we can use. And now here's a bit of a problem. If we look at a full firmware image, more a detailed view will be coming later. Usually those are very, very different from vendor to some other platform, maybe even, or just among OEMs doing the same platforms and vendors all over, but having still their own approaches in various ways. And there is quite some other factors which then come on top of that. So one example could be applications that are running then on top of that, which may need to interact with firmware. So building tools is actually a very huge investment, and that can sometimes not be the case when you have a very small and specific purpose-built tool. But at large, I think the statement actually holds, and especially in terms of software. So to give one example, which may be a bit more intuitive if people have worked on applications, if you want to create a new mobile applications, be it for Android or iOS these days, for example, there is a huge amount of setup that you need to do. You need to register for platforms, need to create different accounts, especially if you want to integrate with the operating system more and more. Then you need to know all the specific APIs. And the same is true in very many other spaces, just like in firmware. So we know two very large platforms, the Intel and AMD x86 platforms, which already have their different approaches of building a platform these days. So from Intel, we know there is a concept called IFD, the flash descriptor, which is basically just a partitioning scheme for a flash image. But in reality, of course, that means we still need to have this very specific implementation. We can't just use some partitioning tool that we would otherwise use for, let's say, a hard disk in the same manner. We would need a specific tool for that. And then there is their ME sort of file system. So there is also something built in. Eventually, if you look at firmware, you always have this impression that it's sort of a matryoshka. So you have something that is actually part of something larger and larger even, but usually you start on the outside. So you start uncovering, and then you always find more and more and more pieces inside. And that is also true for UEFI. In a UEFI volume, you can find lots of different things. And that is something we will be looking at in a bit. On AMD platforms, we have similar things. So we also use UEFI these days, and then everything for the platform itself is integrated through a thing they call PSP, the Platform Security Processor, or nowadays just the AMD Secure Processor. But that is what is starting the platform, and so it also defines certain data structures, which have something like a concept of directories and so on. There is special other firmware for the SMU on their platform and so on. And then, of course, there's lots of other platforms. There is ARM, RISC-V, and Extensa and whatnot. If you are familiar with those single board computers, of which you can get hundreds of different ones these days, you may also have seen that basically every vendor has their own sort of protocol that is run over either USB with a special bootloader or through some other means of connection. So tools, we already have lots of other tools, which I started looking at for editing firmware. And this here is really just a very small and concise list so that it fits on one slide. But what I'm trying to say here is these are now very, very specific purpose tools, which we can leverage in a more overarching concept. And that is what Fiedka strives to do. And the other thing is, most of those tools really just have a very narrow concept in terms of user interface. It's mostly just trees and tables, and maybe some colors, just like in these three examples that we can see here. but I'm arguing that we can do a lot more actually. And so I already gave a talk last year at the Remote Chaos Communication Congress, of which you can also look at the recording, where I explained a bit more on my view on user interfaces and what we can actually learn from the web developers to give us richer capabilities for firmware and also maybe other projects. So a few general concepts that we find in firmware is, first of all, the hard part. We have multiple phases or stages which are involved. So the platform is starting at some point. There is some processor doing some initialization, and then it's handing over to some other processors. Like on the Intel platforms, the management engine is starting up the platform. At some point, it's handing over to the x86 cores. And then there may be a few other smaller microcontrollers involved on the platform to assist with, for example, power management, or on laptops, we know embedded controllers and so on. There's a lot of stuff going on there. And that also means that we're handing over lots of payloads where we need to be very careful, and we're building up chains. However, I'm not going to derail too much into security here. I'm just aware that we have all of these components involved. And that second thing is the volatility or non-volatility of the platform. There is a lot of things that can also change. So there is configuration, which can be changed at runtime. And there are also binaries which can be changed at runtime, which is basically what we know as whatever is in your SPI flash on your laptop, for example. So there is something also that we can persist for a while, but we can still change things. On reset, things may look a bit different again. One example, which is something that we very rarely look at, for example, is the DRAM configuration. So when you boot up a machine and you have some DRAM module in there, the machine will be trained for it. There will be some information persisted for a while. When you reboot the machine, you will see the same thing again, unless you insert a new DRAM module, then you would see something new again. So that means your firmware image will change, even though you made no other actual changes to the platform. And for analysis purposes, it can get very interesting, because now you're seeing some volatility where you may not even expect it. But let's look at the easy part first. So we have this concept of storage, and we have the concept of files. We know that from operating systems, that's where we came up with the idea of file systems. And what file systems allow us to do is we can look at chunks of memory basically in a very, very simple manner. We just define it's a sort of just a stream of bytes basically. And then we put some metadata around it, give it some properties, and that's about it. But for us here on firmware platforms, it's the inputs to our boot flow in part. So it may be that we have a modular system, just like with UEFI, where not everything is necessarily involved all the time. But there is still lots of different inputs. So we have a lot of volatility when those change over time. And that brings us to the current state of the Fiedka application. This is how it started. I was talking to Ryan last year at FOSDEM, and he showed me something he called IUTK2. I think the I is for interactive, and UTK is the UEFI toolkit that we have in the Fiano project from Linux Boot. That is a tool which is, well, basically an analysis tool, so you can look at what is in a given firmware image, but it also has the capabilities to edit that image and rework it. So for example, you can remove something that you don't need, like Dixie drivers, or you can insert whatever else you want, like UEFI Doom, for example, if you want to play a game in your machine, or maybe Linux Boot because you want to leverage your Linux developers and have them write your custom bootloaders. So the first step I did was really just then to do this very simple thing I described a bit earlier, to render the flash usage of an image. So for reference here, we're looking at a very small image. It's just 2 megabytes here in the screenshot. And you can see all the red blocks, which is basically what is the used parts. And then there is the free parts. I also did the visualization for the 0 blocks, which is something that may give you the hint that there is an area in the flash which is maybe used for a configuration or something like that. It can depend. And I did all that just doing a very simple proof of concept web application, which I then called UTK Web. And well, I was really just rendering fixtures. So I was just dumping from the fmap tool that is also part of Yano. And that gave me some JSON output, which I could then load into the web browser and make it look like boxes and colors and so on. And that is basically also my main field of expertise, what I'm doing for a day job. As a web developer, I mainly just translate data into something visual. And well, for interactive parts, then I just register some event handlers. And for the ugly part, I need to do some state management when I make some changes. But that's roughly the summary of what web development actually is in the front end. So I did a first draft, and then Ryan asked me if I could also make the color suitable for colorblind people. So I derailed a bit. But anyway, here we go. I ended up with a color palette which has even more colors because we will need them at some point, which is suitable for people which have different perceptions of contrast and so on. So it's all accessible. Now let's have a look at a small demo. This here is UTK Web currently deployed just as a static website. And what we see here is an image that I loaded from one of the machines I own. On the top here, we have 4 different tabs from different tools from which I took the fixtures. So there is UEFI firmware parser, which you might have come across already, to which I contributed the capability to output its data as JSON instead of tables, so I could load them here. And I did the same thing with UTK's output. UTK was already capable of giving me JSON. And then I added the same capabilities to PSP tool and also MFT, that is Memoya's firmware toolkit. So on top here, I can just switch between the tabs to get different views. And that is actually very important because we need to be aware that when we look at this here, which is currently the UEFI part of the image, it's a very, very different view from when we look at, for example, so this here is an AMD platform where we look at the PSP data structures. And we will see something very interesting about that in a bit. So down here, I basically have something which you may know from a desktop as directories. When you have a file browser, you can have directories, you can nest them, and you can do the very same thing with firmware volumes. So here, each of those directories is actually flattened so that we don't have a tree, but we have a simpler structure. And I did that because we only have a very few directories. And I can still retain the references so that I can always build up the tree again if I so wanted. There is a quick navigation on top here, so I can click any of those buttons to jump down to somewhere else. Let's say, for example, here. And if it's one of those nested firmware volumes, I can actually jump to whatever would be inside there. Let's say here. This here is a very small firmware volume. It's something that you mostly know for legacy support, the so-called CSM, so the compatibility support module. That is a concept in UEFI to also boot older operating systems or boot without the UEFI capabilities, basically. So currently what we're displaying here is the size. I'm also referring to something like a block usage here, but it's actually a bit misleading because the file system in UEFI is usually compressed. So this is not really the amount of blocks it's using. That's what it would be using if it was uncompressed. Anyway, you can look at some metadata. The depx, that's dependency expressions here, they give you a hint how this module is also in a certain relationship with something else. I added a few other hints, like the little car here, for example. That's what you see for drivers. And then there is also some other parts where we're not actually sure yet what they are. So sometimes we only find UIDs, which are unfortunately not very human friendly. And we have these freeform modules. So this might be interesting. If you see something that looks suspicious, then maybe that's something you would want to extract and then reverse engineer for security purposes. So let's have a quick look here on the right-hand side. You see the flash as it would be. And you can see that, well, about more than half of it is actually used. So that means you have still quite some space. For example, if you wanted to deploy Linux boot, but maybe you would want to make some adjustments so that you have some contiguous space down here. So that is something that this view can help you with. So at least now you know the addresses where things are, so the offsets within the flash, and then you can make your readjustments. That is not yet a capability we have here, but it's something maybe to keep in mind for the future. And now let's have a quick look at the PSP view. So in PSP, you can already see when I'm hovering here, you see some bits and pieces highlighted on the right-hand side. We also have this concept of directories and entries, and now we can see exactly where one of these binaries, which you see on the left, is in the flash, which you can see on the right. This can be very interesting for some purposes. For example, if we can do the reverse at some point, then maybe we would just like to highlight a section and see what's actually in there. Anyway, this here is from PSP tool. We need to be aware that AMD's documentation is currently not very public. We have some bits and pieces in the core boot documentation, but it's referencing NDA documents. So we do not have all the knowledge to visualize everything, which is a bit different for UEFI, which is a mostly open standard with some vendor-specific, let's say, flexibilities. Okay, let's get back here and see how it's currently going. So at the moment, Fiedka is an application which is based on a toolkit called Electron. Electron is basically just a Chrome web browser wrapped up in Node.js, and that can then be just run on a desktop. And because it's based on Chromium or Chrome, which is ported to many different platforms, we can actually run it on Linux as we used to, or on macOS or Windows if we wanted. It's not set up yet in the project that we have on GitHub, but maybe if somebody would like to chime in, it would be great to also have the other platforms supported. The backend that you have in UTK, that you have in Fiedka, which is coming from UTK, is based on a concept called WASM or WebAssembly. So that means it is running in the web browser. You have a file picker, like here in the screenshot. And that means everything that is being processed to get this analysis here is just running for you locally. So you don't need a remote server to do anything for you. It's just happening on your machine, which is very important for, let's say, if you have proprietary images that you cannot just expose somewhere else. We have already looked at the UI components that we have. So we have these directories here with their entries. We have the flash usage or fmap, and we have the navigation on top. What I haven't yet shown you is the search, and that is something we will have a look at in a bit in the next demo. For development, there is something set up called Storybook, which is a prototyping environment where you can develop UI components. Now, these are the integrations that we currently have in the main branch. There is UEFI parsing through UTK, what I just described to you. There is an experimental branch for analyzing PSP, which is based on the converged security suite from 9-elements. There is a draft for rendering a TPM log, which you can see down here in the screenshot, which is based on fixtures from TPM tool. And I also looked at a few other tools. There are also some pull requests open to TPM tool. Maybe that's interesting for you to look at. And with that, let's have a look at another demo. And I'm sorry, I had to use a web version now. So this is currently not really the Electron application, but it's conceptually the same. It's due to the setup here. Anyway, we have a file picker, so we can select the file. And let's use something we are mostly familiar with, and that would be the OVMF, or Open Virtual Machine Firmware. There are nightly builds, which you can download from Red Rage's GitHub, for example. And this is also what I took here. And so now you just got a live analysis of what you find in that very image. On the right-hand side, we have the flash usage, as we just saw also in the previous version. And here on the left, we have our images again, or the directories. I'm sorry if everything is a bit in a small font here. It's also due to the setup. However, I would like to show something now. So first, let me hide the sidebar here and make it a bit larger. And now let's do something which can also be very interesting. Let's say we want to search for something which is part of PEI, the pre-EFI environment. Then we can just type here in the search, and immediately we find, first of all, we know in which directory it is. And then also we just have the view reduced to whatever includes that substring PEI. We can also search for other stuff. For example, if I know a GUID, let's say something that starts with 222, I can also type that, and then I will find that specific entry. And I hope this will make it easier for people to maybe verify that something is indeed in their image. For example, if you're building these images, then it might be very nice. Or if you want to find something that you want to remove, let's say maybe the CSM components that we saw earlier, which you may not need in your current environment. All right. So a bit on the roadmap. The next big milestones will be to finalize the PSP integration, which I just talked about, and then as well as IFD and ME support, as well as core boot file system parsing, which will also be very, very interesting for people working with core boot. There is a tool called CBFS tool, but Fiedka could also give you a more visual view of what the command line tool would do otherwise. But that means there is some backend work required here. Then the edit and save capability. So currently you only can see what is in your image. However, the next step would be that you could also remove something or insert or update parts of the image and then save the image again so that you can flash it back to your device, check, and do something which is more like a continuous improvement way of working. The MVP, the minimum viable product, will be to just delete one of the Dixies in OVMF. That would be very simple because UTK already has support for that. So it basically just takes a button and a bit of state management. There are some ideas around emulation. For example, for binaries which you want to investigate, it might be interesting to emulate them in a monitored OVMF environment. So you could take an OVMF image, create that on the fly, just if you click on something, and run it in QEMU immediately. And then you could monitor whatever it's doing. Maybe you look at the registers which are changing, or maybe memory access and something like that. Likewise, we could do the same thing with PSP EMU, which is also from the PSP reverse project, just like PSP tool, which would allow you to emulate PSP binaries. And I guess we can do so for many different other stuff. UEFI runtime services, maybe a monitor for SMIs might be interesting. That is something that would usually be used for security purposes to narrow down its capabilities, but it might also be interesting just to understand what is happening in SM. That would be the system management mode. Another idea is to create a bootable ISO so that if you have a machine that you want to investigate, you don't need to install the app or maybe lots of other tools, but you have a ready-made image that you can just boot into, and then you can inspect the platform already. That would be very interesting for integrating directly with the system so that you don't just load a file, but you could actually talk to, let's say, your platform controller hub and obtain the firmware image from there. So that would make it sort of the counterpart to Kali, which is a very famous security-focused Linux-based operating system to do lots of different things. One possibility would be to extend the system rescue CD, but that's just an idea. Then talking about system integration, one neat thing would be to also work with the EFI variables and secure boot. So for example, just looking at the EFI variables, maybe there is a nicer way than just using the Linux sysfile system, but instead have something visual. Especially for entries which are really just binary blobs, it would be more helpful to have some metadata around it, or maybe the interpretation of that, just binary garbage otherwise, which you wouldn't really understand otherwise. Integrating with Go UFI would be very nice so that you can manage your secure boot keys, for example. For TPM, it would be very interesting to display the TPM log. Currently, there is, as I said, a draft for a visualization thereof. I looked at TPM tool. There is also Go attestation, which can be included, as well as the immune guard agent, or maybe TPM.js. So TPM.js is basically a simulation environment for TPM for the web browser, but it could also be leveraged for debugging purposes, for example. So if you have a log and you have all your hashes from your TPM, maybe that could help you a bit with understanding why certain hashes changed a bit different from what you expected or something like that. For the UI and the web stuff, we can do lots of more visualizations, like DMI and SM BIOS, which is basically platform information, ACP tables and device tree, and even the firmware menu. So usually you would press something like delete or F2 when you boot up your machine, and then you see a menu. But there is actually a representation format for it, and we could extract that from an image and also render that on the web, or, well, in the Electron application now. And of course, lots of other stuff like the platform and memory setup. We could look at page tables, interrupts, and MSRs. And somebody just made a very, very nice tool that was Graham Sutherland, which is the CPU ID visualizer. So if you know your CPU ID, you can look at every single bit of it and then interpret what is in there. Here for the web developers, this is basically the API for visualization. So with the firmware volume, for example, that we have from UFI, this is just a very simple function to translate that to something that Fiedka would understand. So Fiedka already has the components to render things, but it would need a certain format. So of course, this here is a bit of a shortcut. You see it's also calling other functions. But basically, this is how I just need to translate data that I have from one system to be able to render it in a unified manner. If you have other ideas, I will always be happy to pick them up. So you can just check out the GitHub space Fiedka and file your issues there. And with that, thank you a lot. And finally, here are the links to the project website, the slides, and the previous talk I gave last year.